Hello, my name's Thanom and I'm from UNSW. Today I'm working through some of the MATH1011 calculus problems from the section on differentiation 2.3. This is question 16, which is about the motion of a particle in 2 dimensions here. So we're given the displacement vector. So this displacement vector, I just want to rewrite it here so they're all in a row. So the displacement vector according to time is 1 plus t in the I direction and t minus 2 all squared in the j direction. So part A asks us for the velocity and the acceleration at a particular time. Well, first of all, we need to determine the equations for the velocity and the acceleration, and then we'll plug in t equals 1 after that. So remember, velocity is just the derivative of displacement with respect to time, but this time we differentiate component-wise. So 1 plus t differentiates to 1, and t minus 2 all squared differentiates to 2 outside of t minus 2 to the power of 1 times 1, but we don't need to write that, and that's in the j direction. So this is my expression for the velocity of the particle at any given time. And remember, acceleration is the derivative of velocity. So 1 differentiates to nothing with respect to time, plus 2t minus 1, that's just going to differentiate to 2 with respect to time. Okay, so these are the expressions in terms of time of the displacement of the particle, its velocity, and its acceleration. Now if we want the velocity and acceleration when t equals 1, we plug in t equals 1. We might as well work out where it is at t equals 1 as well and work out its displacement. So at t equals 1, we're at 1 plus 1, so 2i, plus 1 minus 2 all squared, that's minus 1 all squared, which is 1, so that's plus 1j. So we're at 2i plus 1j, or perhaps you'd prefer to write that as 2, 1 in a column vector form like that. The velocity at time t equals 1, when I plug, there's nothing to plug t equals 1 into here, it's 1i. Plus, when I plug t equals 1 into here, I get 2 lots of minus 1, which is minus 2. So minus 2 in the j direction, or if you prefer 1 minus 2 as a column vector there. So that's its velocity. Its acceleration is 0i plus 2j. No matter what, its acceleration is always that. So its acceleration after 1 second is still the same, 0i plus 2j, or if you prefer, 0, 2, written like this. So the displacement is where it is after 1 second, how fast it's going after 1 second, and that includes the direction of the velocity, and the acceleration after 1 second. Now we want to put this on a diagram indicating what's going on at t equals 1. So let's see what's happening. So at its displacement is where it is. So after 1 second, it happens to be 2 in the I direction, 1 in the j direction. So I is often the horizontal and j is the vertical, so we'll stick to that. So 2 in the I direction, 1 in the j direction. The particle is here at t equals 1. That's where the particle is. We could draw a position vector there for where the particle is at t equals 1. Sometimes that's a little bit confusing putting the arrows on for these as well, but we can put it on there. So that's where it is, that's its displacement. In fact, I might write displacement. Now, its velocity, so its velocity is a vector, it's 1 minus 2. So it's 1 in the I direction minus 2 in the j direction. I could draw that velocity vector starting at the origin, 1 in the I direction minus 2 in the j direction, and it would be a vector down here. But it makes a bit more sense, I think, starting where the particle is. So 1 in the I direction minus 2 in the j direction is a vector in this direction here. So this is its velocity. This is at that moment in time, it's traveling in this direction. And if you wanted the speed, you would calculate the length of this vector. So the speed would be the square root of 1 squared plus minus 2 squared. So actually it's travelling at square root of 5 meters per second, say, but it's travelling in this direction here. So that's its velocity at t equals 1. And lastly, the acceleration. So you can kind of think of acceleration as a force. Force is mass times acceleration. So this is kind of the force that's making it change its direction or making it speed up or slow down. So that's in 0 in the I direction, 2 in the j direction. Again, you could draw the vector at the origin, but it makes much more sense, I think, to draw it where the particle is. So this is my acceleration. 2, 0 in the I direction, but 2 up in the j direction here. So this is where the particle is, this is where it's in the direction it's travelling in, but the force is moving up at 0, 2. In fact, the force is always like that. Now, we can make a little bit more sense, I think, of the diagram if we work out the Cartesian equation of the path that the particle is travelling in. So let's do that. So here, I guess the x-coordinate, the I direction, is given by 1 plus t. And the j direction, or the y-coordinate, is given by t minus 2 all squared. We can eliminate the parameter t, and we can see the path in terms of x and y that the particle is travelling in. So if I make t the subject in the first one, so according to equation 1, t is really just x minus 1. And then if I plug that into 2, substitute into 2, then we get y is really x minus 1 minus 2, so that's x minus 3 all squared. So this is the path that this particle is travelling. Okay, so t is the parameter. At time 1, the particle happens to be there. I could plug in time 0. If I plugged in time 0, it would be at 1i plus 4j, and we would know that at time 0 it was here, and we could also work out its velocity and acceleration there. If I put in time t equals 2, I would get 3i plus 0j, so I would know that it was here at t equals 2. I could plug in time 3, it would be 4i plus 1j, so it would be here. So you can see we can plug in various values of t and work out where it is, but by eliminating the parameter t, the time, I can see the path that the particle is travelling in. So this is a parabola shifted across to 3, and so this will make a bit more sense. I'll just kind of put a dotted line in here. It seems to be travelling in this direction as well, right? Because t equals 0, 1, 2, 3. Presumably if we plug in 4, 5, 6, it will keep going to the right there. Okay, so this makes sense because this velocity vector, that's the tangent line at this point here, and the force, the acceleration is constantly 2j, which, so it initially is coming down, but the force is kind of making it essentially turn around and come back up in this direction there. Okay, so it is a nice idea to be able to put everything together into a Cartesian equation there. So here's the path that the particle is actually travelling in. So that's question 16.